In this video, we're going to define the radian, angular displacement, angular velocity, and angular acceleration. So the first thing that we need to discuss when we're talking about rotational motion is imagine we have an object like this, and it rotates around some fixed point here. So let's say it's rotating around like this, and this is what we call a rigid body. So this is a rigid body, and what we mean by that is that as this rotates, so let's say it rotates up through some angle, comes up like this. As it rotates, all the points remain fixed relative to each other. So the red point rotates up to the red point, and the green point rotates up to the green point here. So that way, if these are all on some line like this, then they remain all kind of within a line after they rotate up. So all the points remain fixed relative to each other if it's a rigid body. And this is the only type of things we'll talk about rotating. We won't talk about anything that's kind of moving like the green points move separate to the red points. We'll have everything moving fixed. So as this rotates, let's say that we had it here at some initial angle, we'll call it theta initial, and it rotates up through some final angle, we'll call it theta final. Now, as it rotates, we see here the path of the red part, part of the mass, that path is much longer than the green here, and that's because the red is much farther from the point it rotates, or what we call the axis of rotation here, or the point of rotation, or the pivot point. So we'll call this axis of rotation, or pivot point. And so because the red point is so much farther from the axis of rotation, then it rotates a lot farther. So it becomes very difficult to talk about a linear displacement, because clearly the red one went farther than the green one, and some other point in between would again not have the same linear displacement that either of the other points had. But we do note, however, that if these points all lie along this initial angle theta initial, and then they all lie along this same angle theta final, we do note that they all go through the same change in angle. So they all go through the same delta theta. So it's much simpler with rotational motion to talk about an angular displacement as opposed to a linear displacement. So we define that angular displacement as angular displacement as simply a change in the angle, so a delta theta. Okay, so we have delta theta is our angular displacement. And so there's a few ways that we could look at this. We could say, or a few different units we could give this delta theta. We could call it degrees. We could even call it revolutions. But typically, we will measure this angular displacement in a unit of angle, which is called a radian. So a radian. We use RAD, rad for short, oftentimes. So a radian. These are typically our units of angular displacement. So what is a radian? A radian is, let's say that we have a particle here on the edge of this path, and it moves through, as it goes through some angle, this particle moves along some path, and this path is the arc length we'll call S. So this is the path S. And then, of course, there is some radius associated with this as it goes around the circle or even just an arc. This is our radius r. And we define a radian as the angle. When an angle is measured in radians, this is that arc length divided by the radius. So this is the angle measured in radians is the arc length divided by the radius. So you can see here if the arc length is equal to the radius, then we have 1 radian. So if S is equal to R, then we have the angle theta is equal to 1 radian. And we know that we have in 1 full revolution, then like if we go all the way around the outside here, and we go in 1 revolution, then we have the arc length would be equal to the circumference, which is equal to 2 pi r. We know this from our math classes. So the arc length is equal to 2 pi r when we have 1 full revolution. So this is for 1 revolution. But the arc length is equal to r theta when the angle theta is measured in radians, and that this is equal to 2 pi r. Then we see that the angle that we have in 1 revolution is equal to 2 pi radians. So the angle for 1 complete revolution is 2 pi radians. So we have 2 pi radians in 1 revolution. So if we wanted to convert, let's say we have degrees or something, we have let's say 45 degrees, and we wanted to convert this to radians, and we would say, well, we have 2 pi radians in 360 degrees, right? Because we have 2 pi radians, we also have 360 degrees in 1 revolution. So we multiply 45 degrees by 2 pi radians per 360 degrees, and we would have pi over 4 radians. This is how many radians there are in 45 degrees. Okay, so when we define it, this is very important as we get into later stuff. We need to use radians when we're talking about rotational motion because of this fact right here. If the arc length divided by the radius is the angle measured in radians, this means that our arc length is equal to the radius times our angular displacement in radians. So as long as we use radians, we can use this fact here. S is equal to r theta. Okay, and we can always convert knowing that we have 1 revolution is equal to 2 pi radians, which is equal to 360 degrees. We can always convert between degrees, revolutions, and radians with this. So 2 revolutions would be 4 pi radians, which is like 12.5 radians. Okay, so now that we've defined angular displacement and we've defined our units of angular displacement, which are radians, let's move into angular velocity. And the way we define angular velocity and angular acceleration is the same as we define them with linear terms as well. And so if you remember back, we said a linear velocity was equal to a linear displacement over a time, right? And the units of this were in meters per second. But in rotational motion, we will define an angular velocity using an angular displacement as opposed to a linear displacement. So if we have here, we have an initial time at an initial theta, and then we have a final time at a final theta. We have a angular displacement in here, so this is a delta theta. And then we have a delta t as well, so time initial and time final. And we define our angular velocity with this. So with these units. So angular velocity, actually sometimes this is called rotational velocity, so angular slash rotational velocity. And we use, to symbolize angular velocity, we use a Greek letter omega, so like a very curvy W. So this is a lowercase omega. And angular velocity, or rotational velocity, is defined to be our change in angle over time. So very similar to linear velocity, which was a linear displacement over time. Angular velocity is an angular displacement over time. The units of this would then be radians per second. We use radians for our angular displacement, or we could, another common way to refer to angular velocity is in revolutions per minute. Knowing we have 2 pi radians per revolution, we can convert between revolutions and radians, or technically we can even use degrees per second as well. We would just then need to convert between degrees and radians. So the units of angular velocity are radians per second. This is the important one to use, and is defined as just an angular displacement over time. And then rotational or angular acceleration is defined very much the same way. If you remember back when we had a linear acceleration, this was a change in a linear velocity with time. For angular acceleration or rotational acceleration, we use a alpha. So this is the Greek letter. This is a lowercase alpha. And it's defined very similar. We had for linear acceleration, we had a change in linear velocity over time. For angular or rotational acceleration, we have a change in angular velocity with time. So delta omega over delta t. And the units for this, we have omegas in radians per second. Time is still in seconds, so this is radians per second squared. Or we could have other kind of interesting units like revolutions per minute squared or degrees per second squared or something. But what we need to use is radians per second squared, and this will be important in later videos. Let me lastly talk about these are actually all vectors. Alpha, omega, and delta theta are all vector quantities, and we use the same notation that we use for torque. So if we have counterclockwise rotation, this is a positive angular displacement, and this is a positive angular velocity and a positive angular acceleration. So, and this is something speeding up. We've talked about what alpha is for is something speeding up as it goes around a circle. We've talked about things going around a circle with a constant velocity or a constant speed, but now with alpha, these things can start speeding up as we go around a circle. So the positive direction is counterclockwise, and real honestly, this all just comes from if delta theta is positive in the counterclockwise, clearly omega and alpha are as well. And for the negative direction, this is negative, so delta theta is negative here, omega is negative here, and alpha is negative here. So same sign convention that we have for torque, in which counterclockwise is positive and clockwise is negative.